Hello everyone. Here we have an interesting question of projectile motion and the radius of curvature. A particle is projected with speed u at an angle theta with the horizontal as shown. At some general point P, the radius of the curvature is proportional to the cos phi to power n, and this n is an integer. Our task is to find the value of n. Got the question? I urge you to post your opinion, your answer in the comment box, and let's proceed further for the detailed solution. The correct answer will be n is equal to -3. We already know the formula of the radius of curvature. The radius of curvature is v square by a normal. Actually, at this position, you can fit a circle, okay, and the radius of that particular circle will be known as the radius of curvature. This is the radius of curvature at point P. Got it? Now, to get the A normal, what we do, this G, acceleration due to gravity, will do its components. One component along the tangent to the path and another component along the center of the circle. This component along the center of the circle is known as AN. So the computation is pretty simple. Here the angle is phi. So the G has a component along the radial direction G cos phi, and this tangential component of the G is G sin phi. How we got the angles? This angle is phi, and the tangent and the normal, they create an angle of 90 degree. So here the angle was 90 degree minus phi, and this total angle was 90 degree. So this must be phi. Got it? Now, putting up the data in the formula, the speed is v. So we'll keep it v only, v square divided by the acceleration, which is normal to this path at this point, is g cos phi. Got it? Now we are going to obtain that v in the terms of the given parameter u and theta. How we can do that? The v has a horizontal component here. This component, we'll call it v cos phi. And you remember, in this kind of projectile motion, the horizontal component remains unchanged for the velocity. It means the u cos theta is technically equal to v cos phi. Do you agree with that? There is no acceleration in the horizontal direction, so this speed in the horizontal direction is actually constant. From here we can obtain the value of v. V is equal to u cos theta divided by cos phi. So I am submitting the value of v here, which will be equal to u square cos square theta divided by, we are left with g cos cube phi. You understand this? V square, then there will be a cos square phi term. One cos phi was already there, so cos cube phi. Why we have done that replacement? Actually, v here is variable. At this point, at this point, at this point, the data of v will be different, as well as the data of phi will keep on changing. We need the proportionality of r in the terms of phi. So now in this expression, if we pay attention, this entire data is actually constant. U is the initial speed. The initial speed is a constant. At a given moment, the initial speed is constant. Later on, the v is the variable data. The v has the initial value equal to u. Clear? V is variable, but u is constant. This theta is constant, g is constant, only phi is the variable here. So we got the required relation. The radius is proportional to cos phi to power -3. So the answer is -3. Okay. Now we can obtain the radius of curvature at any point of this parabolic path. Suppose I name this point as, let's say, 1, this point let's say 2, this point let's say 3. If I ask you what is the radius of curvature at the position 1, what should be your answer? It's simple actually. At the position 1, in this general formula, the phi will become equal to theta. Put phi is equal to theta in this general formula. What is the answer? It comes out to be u square by g cos theta. What is the radius of curvature at the position 2? At the position 2, we know the velocity vector will be directed like this, horizontal. So the phi with the horizontal will become 0. Put phi 0, the result will be u square cos square theta divided by g. And we can verify these results. At the top, if you check, the speed here is u cos theta only, and the acceleration in the normal direction to this path is g only. So this expression comes out if we use this formula, and same calculation we can see here. If this is g, the acceleration in the tangential direction is g sine theta. Acceleration in the normal direction is g cos theta. I hope you get this also, because this angle is theta. Here is theta, this was 90 minus theta, and this is theta. So if we go from bottom to top, what happens to the radius of curvature? The radius of curvature is actually decreasing. At this point, the top point, the radius of curvature is minimum. Okay, and as we descend down from here, the radius of curvature again increases. So we can summarize that ROC is minimum at the sharp turnings, and here the radius of curvature is greatest in this case. Stay awesome. See you again.